Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a physicist, I love being a scientist, and I really enjoy chatting to everybody about all of the cool things I get to work on. So for anyone who's not familiar with Cup of Cosmology, the idea here is that this is an interactive stream. So you people can ask me anything you want, and I will try to answer. You can ask me about academia, about space, about physics, about cosmology, about Finland, basically anything you want, and I will do my best to answer. Now, of course, I don't have all the answers, but I will try to answer your questions. I see we have some of the regulars coming in. David, Brath, Anne, James, Scott. Great to see you all, as always. Welcome back to all of the regulars. Welcome if you're a first-time viewer. I see we have John, we have another David. Oh, no, same David. Okay, said hi to David twice. That's fine. We always have multiple of Davids in the room anyway. So, yes, welcome. There's the other David. See, I was just preempting getting a second David in the room. Welcome back to all of the regulars. Welcome if you're a first-time viewer. If you haven't done so yet, please do subscribe to the channel, leave a comment, like the video, do all of the usual YouTube stuff. It really, really does help boost engagement. And it helps me get more audience, so then more people I can talk to about all of the cool things that happen inside the universe. I see we have a bunch of people coming in saying hi in the comments. Always nice to see you all here. Really, after the streams end, I always check like how many comments I've received, and I'm always impressed by just how chatty you all are, and I love that. That is the point of this stream. Everyone here is welcome to ask questions. Doesn't matter if you're a scientist, doesn't matter if you've never touched science. Wherever you're coming from, you are welcome on Cup of Cosmology. You are here to ask questions. I'm here to answer questions. This is how the streams work. Okay, so today, rather than doing a general Ask Me Anything, we do actually have a topic today. It's not just going to be me rambling about random stuff, which is the usual thing. It's going to be me rambling about a specific topic. This is weird. Just heard my doorbell. Was that my doorbell? Did I imagine my doorbell? I might have imagined my doorbell. Okay, that's who's ringing my doorbell on a Sunday evening. I probably imagined it. Just let's assume there's nobody there, and I'm not going to go open the door anyway. So that threw me off. We do have a topic today. As I was just saying, today is not just going to be random, ask me whatever you want. Today there is actually a specific topic. And as you've already seen with the title of the video, that topic is, drum roll, the perturbed universe, which makes no sense. That was deliberate. I'm not doing clickbait titles, but almost there. So perturbed universe, basically we're going to do perturbation theory applied to cosmology. Now, this is a really cool topic. This is something that is going to be very fun to break down. So just to give you an idea of what you can expect today, we are going to understand, we're going to jump into things like, where does the cosmic microwave background radiation come from? Like this here, this oldest light in the universe, less than 5 minutes today. This map here, the oldest light in the universe, this has temperature differences, blue spots, orange spots. Today, we're going to go into detail about where these come from, why there are orange spots, why there are blue spots, and the significance of this. We are also going to cover the big question that's in the prompts here. Why are there galaxies in the universe? And by extension, why are there planets? Why are we here having this conversation? Which seems a bit philosophical, but at least on a basic level, I'm going to cover why there are galaxies, why the CMB looks the way it does, and how we mathematically describe all of these things. And it's going to be very fun. Now, I see there are comments about my shirt, and that is funny because my shirt doesn't just say I can't even. There's more to it. But I realize that with the camera angle, I look like I'm just being kind of like the basic online girl. I can't even. There is more to the shirt. It doesn't just say I can't even, but I love that the camera cuts it off as saying I can't even. The full shirt says I can't even think straight. It's one of the many queer shirts that I have, and I love this shirt. And yes, I've just realized it with the camera angle. I'm just like, oh, I can't even. And that amuses me. I've also realized that with the current camera angle, as some of you might know, as of last week, I have a new setup, I have a new angle, everything's a bit different. I actually finally today got around to putting up a picture that I've been meaning to put up for about 6 months. The picture is just out of frame. I was expecting it to kind of be here, but the hooks were higher than I expected. So there is a picture up here. I put it up today, but it's out of camera. So that didn't work out how I was planning it. So at some point, I think next weekend, I'm just going to put a plant here. So then there's something in the background and it's not just this big white wall in the background. So then there will be some more details. But yes, if I hit the table, the camera shakes. That is good to know, good to be aware of. Okay. Yes, depending, because of the mirror image, you might be reading my shirt backwards because I do have the mirror set on the camera, because otherwise it's extremely disconcerting. We're so used to having our cameras be mirrored that if they're not, it just looks weird to me. So because I see myself, I have a big box showing me exactly what you're all seeing. So if I flip it so that you can read stuff, then it just looks wrong to me. So yes, it says Tanakai. That's what the shirt says. Okay, so today's topic, perturbation theory. Yeah, you just realized the image is flipped. Yes, because I have the camera mirrored on. I have just realized that it is very warm in my apartment. Okay, if it's a picture we cannot see, we'll call it the dark picture. Yes, if you can't see something, just call it the dark picture. There is a picture up there. It is dark. It is the dark picture. It does not occupy 25% of my wall, but there is a dark picture there. Hey, Arlo, welcome back. I know you were here last week. Great to see you again. Great to have you here. So today's topic, the perturbed universe. This is going to be a breakdown of perturbation theory and how perturbation theory applies to cosmology. Now, there's a fun challenge for me this week because there is a rule on cosmology that I do not show you equations, I do not show you math. Occasionally I break this, very, very occasionally, but I feel like a lot of people think math is scary, and that is in large part because of the way mathematics is taught in schools, where it's taught as kind of like this numerical imposition, and I feel like mathematics makes people kind of scared, and if I just start showing equations, people are like, oh, this is not what I'm here for. So at some point I decided that Cup of Cosmology is an equation-free show because I should be able to explain things without relying on mathematics. Now the fun thing comes that perturbation theory is actually a mathematical concept. So today we're going to do perturbation theory with no equations, which is fun because it's forced me to really, perturbation theory was the backbone of my PhD thesis. The way I wrote about it in my PhD thesis was, let's derive everything mathematically from scratch. We are not doing that today. We're just going to talk about what it means. We're skipping the math. But if you Google perturbation theory in cosmology, the first thing you find is like 50 different lectures of people going through the math. So we're not doing the math today. So first question, of course, big first question, what is perturbation theory? So glad you all asked. So perturbation theory is a mathematical tool that allows us to break down a complex problem into a solvable part that we already know the solution to, plus some changes. So if you encounter a brand new problem that you've never seen before, rather than just tackling it from scratch and coming up with new ideas, what we often try to do is we try to relate this problem with something that we already know how to solve, or something that we already know how to deal with, because it's something that is established. And if the new problem is a variation on the old one, why do I need to reinvent a solution? And I'm going to use an example that I'm going to use throughout the stream. That said, I have not completely thought this example through, so bear with me here. So if you want to make cookies, now let's start with bread. Say you want to make bread. Basic ingredients to make bread, you're going to get water, you're going to get flour, you're going to get yeast, you're going to get salt. You're done. Basic bread. Anything you want to make on top of that, you're going to change it. You might modify the recipe, you might change the type of flour, you might throw in olive oil if you're making focaccia. There's 1,000 ways you can make bread, but they all boil down to having probably water, flour, yeast, salt. 4 ingredients, you're done. Okay, so now let's imagine I ask you to make a new type of bread that has seeds in it. So it's a normal bread, but I want a sprinkling of seeds, just because I like fancy bread with seeds. Now, you're not going to come up with a whole new way of making bread just because I now want seeds in it. What you'll probably do is start with your basic bread recipe, and then ask a question of, okay, how can I modify this basic bread recipe to incorporate the seeds? And what you might do is just make your bread as usual, and then as a last step, you throw in a handful of seeds or 2 handfuls of seeds. We have bread with seeds, and we didn't reinvent a recipe. If you're more of a sweet tooth kind of person, we can do the same with cookies. Now imagine I have never baked chocolate chip peanut butter cookies. This is not true. This is my favorite cookie to bake, but hypothetically, let's imagine I know how to make peanut butter cookies, and someone requests peanut butter cookies with chocolate chips. Now, even though the end product is going to be different, I'm not going to reinvent a whole new recipe. What I'm going to do is take my peanut butter cookies recipe and throw in chocolate chips. So you start with something you know, and then you make a small change to it. Of course, you might have to make other changes. You might maybe need to change the amount of sugar to balance. You might need to add a bit of extra liquid to balance the chocolate chips. But you're not going to start with a brand new recipe. You're going to start with the recipe you know and just make changes to it to get the new recipe. So this is what we basically do with perturbation theory. We get a new problem and we break it down into the solvable part and the perturbed part, the perturbation part. In the case of our bread, the known part is how to make basic bread. Flour, water, yeast, salt, basic bread. This is the solvable part of the bread recipe. The perturbation part are the seeds. This is something new. This is something different. This is how we're modifying the recipe. So you take your bread making problem and you break it down into the solvable part, which is the basic bread, and the perturbation part, which is the seeds you've added into the bread. Now, as always on Cup of Cosmology, if anything I'm saying is unclear, please do ask questions. Feel free to follow up if something's unclear. Let me know. If something of the way I'm explaining things is not working for you, please do let me know, and then we can try to adjust it. But I'm going to use this bread with the seeds analogy throughout or at some point I'll probably drop it, because I think it's something that we're very used to. Maybe even if you haven't baked bread, the general principle behind it is something that hopefully makes sense. Okay, so the problem comes if instead of just saying I want seed bread, I say I want one of those like really thick, dense breads that every mouthful contains a huge amount of seeds. It's just basically seed bread held together loosely with a bit of dough. At this point, you might not be able to do the same thing of take your bread dough and just add a handful of seeds, because you're adding so many seeds that you're going to be missing liquid. You're going to be missing other things. The amount of changes you're doing are too big. So this whole idea of perturbation theory only works if the perturbed part is a lot smaller than the basic part, than the solvable part. In the case of our bread, if I want equal amount seeds and flour, it's going to be quite difficult to start from exactly the same recipe, because you're probably going to want less yeast. You're probably going to want more water. You're probably going to want to do something so it holds together despite all of the seeds. So when the perturbed part, the perturbation part, becomes approximately the same size as the solvable part, then we can't do perturbation theory, because the new part is as important as the original part. So then the picture changes. But as long as the picture doesn't change, we can do too much, we can do perturbation theory. Now, this is something that we apply in a lot of different branches of physics in general, and also in chemistry, in nuclear physics. There's a lot of different areas where this seemingly simple idea of take what you know, make a small change to it, and you get a new solution. This is actually an extremely useful mathematical skill. I'm amused that people now want chaos cookies. Do you feel like this wouldn't work in a chaotic system? Very much depends on how much chaos. So we're considering that we have our base solvable part that we know the solution to. That part is not chaotic. And even if it's chaotic, if we can describe that base part with a solvable set of equations, and then we're just adding some small effects, even if that initial set is chaotic, if we can describe it, we can solve it. If we can solve it, and we change it very slightly, we can do perturbation theory. So this idea underpins a lot of the way we do mathematics to explain different things in the universe, and just beyond the universe in general. There is a joke you might have seen if you like physics jokes, where we make the common joke that everything is a harmonic oscillator. Now, a harmonic oscillator is basically a pendulum. Imagine I have my pen. I should have prepared a pendulum. Imagine I have my pen and I make it swing. Just imagine this is a nice pendulum swinging back and forth. My arm shouldn't be involved. There we go. I have a pendulum going here. Now, this pendulum is something that we know how to describe. It's a harmonic oscillator. This is the most basic system we can think of. It is a harmonic oscillator. Now, when we do a lot of stuff in physics, we often break it down into a harmonic oscillator plus something. For an example, if I have a spring, let's imagine I have a spring here. This is a slinky, but now let's imagine it's a spring. Hey Anna, great to see you in the comments. Nice to have Anna here as well. So imagine I have a spring. The way this spring goes back and forth, this is also a harmonic oscillator. So if I want to describe the motion of a spring, I'm just going to call it a harmonic oscillator. But now imagine, in addition to the spring, this thing here is moving as well. So it's not just a spring going back and forth, it's fixed at one end and moving at the other. And this thing here is speeding up, slowing down, speeding up, slowing down. You can still describe this as a harmonic oscillator plus something else. So there is a joke in physics that the only thing we know how to solve is a harmonic oscillator, because we take the harmonic oscillator and apply that to everything, and that is not too far from the truth. Now, one of the first real applications we had for perturbation theory beyond bread making, one of the first physics applications we had was to describe the motion of the moon, for an example. Now, when you have two systems, I'm going to come back to the harmonic oscillator, just bear in mind that for now we solve things as harmonic oscillators. So let's consider we have a system where we have the Earth and we have the moon. So my head is the Earth, this is the moon. Moon is rotating around the Earth. This is something we know how to describe. Basic motion of one body orbiting another. We have moon, we have Earth. This is what we know how to describe with Kepler's laws of planetary motion. This moon is orbiting around my face, which is the Earth or the planet right now. Now, the problem comes that when we think about the fact that the planet is also orbiting around the sun. So now, apart from the moon orbiting around me, there is going to be a small effect on the moon caused by the way we are orbiting around the sun. Now, this is something you can use perturbation theory for. You take the basic system of moon moving around the Earth, and then you add a small correction due to the Earth moving around the sun. Now, this is going to be a small correction on the motion of the moon, because the moon is very close to the Earth. The gravitational force is very weak. The further away you are from an object, the less you feel the gravitational force. So the moon is going to feel a strong gravitational force from Earth and a very weak gravitational force from the sun. Even though the sun is massive, it is very far away. So then if you want to describe the motion of the moon, this nice purple moon that I have here, that is from the engineering school, the engineering union. I got it at a union march. So if you want to describe the motion of the moon around the Earth, you can do this assuming just two bodies, moon, Earth, moon, Earth, and then you add a small correction due to the sun being over there. This is perturbation theory. We have the solvable system, moon, Earth. We have the small perturbation coming from the sun. This is one of the classical places we apply perturbation theory. So perturbation theory is like divide and conquer. Divide the problem into smaller parts and solve them individually. Yes, basically, and it relies on the fact that you really do need to know the solution to one part of it already. And the part that you're perturbing needs to be small compared to the part that you already know. So you already know this part. We already know how to describe one body orbiting around another. Solving, if we had two suns and a planet moving between the sun, that is very chaotic. That is very difficult to describe. But the Earth-Moon system, we can basically say the sun is a small correction to the moon orbiting around the Earth. So we can apply perturbation theory. Going to questions and comments here. Comment from John. I was reading about perturbation theory some and see the word anisotropies all over. Is that the same thing as perturbation? Is the word not anisotropic? Okay, anisotropies are similar to perturbations but slightly different. So I'll get to that in a minute. That is a very good question, but yes, anisotropy comes from not isotropic, but we'll get to isotropic and anisotropies in a while. That is a great question. Just pin that question. A comment from David Howden here. That description looks like the orbits, makes me think of Epicycle's way of keeping geocentric orbit system. Yes, this is very much something that we do when we're talking about geocentric orbits. We have to take these things into account, but we can use perturbation theory to simplify the problem. But one of the biggest places where we use perturbation theory is in quantum physics. Now, in quantum physics, we have a lot of chaos happening, a lot of randomness happening because of quantum oscillations, quantum effects. Now, if we go down to the quantum world, which just means we're not jumping into a new dimension. This is not like Ant-Man and the Wasp where we go into the quantum realm. That's not a thing. It was a terrible Marvel movie as well. And the bar is low for Marvel movies. And Ant-Man and the Wasp, yeah. Anyway, if we go down to the very small scales where we talk about quantum effects, every particle can be described as a particle and a wave, and everything has these random fluctuations, these random changes. So if I looked at an electron, the electron is not actually here. It's going to be a cloud of probability of where you're going to find the electron, but this electron is going to be vibrating, it's going to be oscillating. And this means that the electron is going to have a wave associated with it. My slinky toy is back to being a wave now. It's no longer a spring. So everything in the universe has these waves associated to it. Every particle in the universe also has a wave. Now, these waves are going to be slightly vibrating back and forth. This is going to lead to what is known as quantum perturbations or quantum vibrations. And this is something that we can describe with perturbation theory. So when we're doing quantum mechanics, you usually take the first description. Let's say my first description is electron is here, but there's a probability that the electron is anywhere in this region here. So then we talk about it as this thing we know plus the perturbation to other areas. And when doing quantum mechanics, it's basically solving tiny harmonic oscillators, back to this idea, because if we have our waves vibrating, we can say, this wave of this particle kind of looks a lot like a spring. It's not a coincidence that I use a slinky toy for both. If I have an electron that has a wave doing this, it's kind of a harmonic oscillator. This also applies when we start talking about electrons orbiting around the nucleus of a hydrogen atom. If you have a hydrogen atom, you have classical picture, you have proton, you have electron going around. Now, this is something that can actually be described as a harmonic oscillator. If you put an electric field on it, you have a harmonic oscillator plus some corrections. So perturbation theory has a lot of applications to quantum physics. If you've ever heard of Feynman diagrams, which is a way of drawing a picture to describe how particles are interacting, you can go to corrections in Feynman diagrams. So this is the main term, and these are the other Feynman diagrams, the other possible ways these particles can interact. This is essentially perturbation theory as well. So yes, you can use perturbation theory to explain quite a lot of things across different branches of physics. But of course, we're not just doing general physics here. We are doing cosmology and perturbation theory applied to cosmology. So the next step is to take everything I just told you about the solvable part, the perturbation part, harmonic oscillators, all of this stuff, and apply this to the entire history and evolution of the universe, leading to us being here today having this conversation. But first, questions. There is a comment here from Arlo. Can we use perturbation theory to explore the sigma 8 tension? That is a brilliant question. And short answer is yes, but no, not technically. And the reason for that is something I will come back to at the end of the stream, because once I go through the whole history of the universe, I'm going to get to the point where perturbation theory breaks down, and then we can recover the sigma 8 tension. If you don't know what the sigma 8 tension is, don't worry, I'll clarify that as well. So that is an excellent question there, Alok. I'm just going to pin that until the end of the stream. So there was a question by Scott here when I was talking about the planet orbiting the system. And Scott said, is it even possible that you'd have a planet only orbiting one star in a binary? No. If you have a binary system of two stars, the planet is not just going to orbit one of them. It will go probably a figure eight between the two, or it's going to draw something erratic. That is very hard to solve. We cannot treat that as just what we know about, for an example, moon orbiting around Earth, plus small correction of the sun. If you have two suns, or two stars, then you're no longer doing a small correction. They're equally important, and so you have to consider them as equally important. We'll not stand by quietly while you slander Marvel movies on this, the opening weekend of Deadpool and Wolverine. Haha, yes. I'm not a superhero person. In general, I don't like superhero films. I feel like there are one or two good Marvel films the rest of them just don't work for me. But I'm glad that people enjoy them. I'm glad that you all enjoy all 25 Marvel movies and 20 series and all of the associated cinematic universe. You know, if you want to enjoy it, have fun. I'm not going to come for you. If you want to go watch Deadpool Wolverine, go for it. I love that there is actually a dog in the film. So, you know, go watch it, enjoy it. Don't let my criticism hold you back. Just personally, I'm not a fan of the Marvel films, and especially not of Ant-Man, where they go to the quantum realm. I will take issue with people going to the quantum realm because people like using the word quantum without having any idea what it means. Yes, it annoys me. Like when people talk about quantum leaps, it's like a dramatic leap forward. A quantum leap is a tiny, tiny thing that you wouldn't even notice. Pet peeve of mine, people saying we're doing a quantum leap when they mean great progress, but what they're actually saying is we took an imperceptible step forwards. Anyway, don't use the word quantum to promote your products. The worst offender, in my opinion, tangent here, I digress, but when do I not? There was a cleaning product, a dish cleaning product called Quantum Finish. And the advert, at least on Spanish TVs, was washes dishes at the quantum level. Yes, you know that's not how detergents work, fortunately. Anyway, enjoy your Marvel films, enjoy Deadpool and Wolverine. Don't come for me. I don't like Marvel films. That's on me. Enjoy the film anyway, but we don't go to the quantum realm. Anyway, back to physics. I see there are no further questions, so we can jump into everything I've just said, but now relating it to the universe. Yeah, I feel like I've ranted so much about the quantum finish that my mother knows about it. So, and yes, I was absolutely ranting about that product because that's happened so many times. Yes, I have ranted about quantum finish, washing things at the quantum level on a yearly basis. Every time I see that product, I'm like, just out of principle, I'm not going to buy that product because that's not how physics works. Okay. So they say electron spin is like a ball spinning, except it isn't a ball and it's not spinning. That is actually quite a fair comment. Yes, we have no idea what words to use to talk about things on the quantum level. Yeah, the dog in Deadpool and Wolverine is actually real. They put out a petition to find the ugliest dog possible to match with Deadpool. Since then, some people online have been trying to find dogs that look like Wolverine so that Wolverine would also have a matching dog. But yes, the dog in Wolverine and Deadpool, or Deadpool and Wolverine, is actually a real dog. And I believe it's a rescue dog as well. But yes, that is a real dog. Okay, so how do we use perturbation theory to explain the entire history and evolution of the universe and everything that's happened in between? So basically, I want to take perturbation theory and explain the evolution of the universe. And we're actually going to start with cosmic inflation. So cosmic inflation is this hypothetical period of exponential growth in the very early universe. Now, anything we talk about in cosmology, anytime we do these ideas of the history of the universe, what we're talking about is basically everything that's come after inflation. Because inflation kind of deletes the memory of anything that came before. So the earliest time we can feasibly talk about is inflation. So I often talk about the history of the universe and I'll say after the end of inflation rather than after the Big Bang, because we can't really talk about anything that might have happened before inflation, if there was anything before inflation. So, inflation, the universe goes from being a very big, very hot, very dense thing to being a ridiculously big, hot, dense thing, but slightly less hot, slightly less dense. So anytime we look at the history of the universe, the dog was voted ugliest, and that led to the casting. I think they put out a call for can we find the ugliest dog, and the one that won the vote got into the movie. So anytime you look at these pictures of the history of the universe, there is this initial phase where things expand exponentially, where everything gets really big and messy. Now that is what is known as inflation. Before inflation, again, we can't really talk about what happened before inflation, but we have ideas of what might have happened. If the universe was much smaller before inflation happened, which by definition the universe should have been smaller before inflation, It could have been so small and so energetic that the entire universe was governed by quantum effects, by quantum fluctuations. So if we go back to our universe before inflation, or just as inflation's taking place, let's say inflation has started, we look at the universe as inflation is happening. The universe has quantum fluctuations in it. Even if it doesn't have particles, the universe has space-time. And on top of this space-time, there can be tiny, tiny, tiny fluctuations. So in the early universe, you have a lot of things doing this, a lot of vibrations. You have a lot of waveforms describing the universe, describing the field that is causing inflation, the energy that is in the universe. Everything there can have these quantum fluctuations. Now, usually these quantum fluctuations are small and don't really matter, and they're just there. Quantum fluctuations are happening all around me, it doesn't matter. But if you have these quantum fluctuations, these vibrations happening in the early universe, during inflation, what's going to happen is these waves are going to be stretched more and more and more and more. So these waves get stretched to the point where we can no longer call them a small effect. So you have your universe that's expanding. These vibrations get caught up in the expansion, and they go from being teeny tiny vibrations to suddenly being about the size of the universe, or comparable to the radius of the universe, because they are stretched so much. Now, at this point, it's no longer a small correction. So then you have a very cool thing happening. As the universe is growing, the event horizon of the universe grows as well. So, yeah, I believe the dog's name in Deadpool is Peggy. That does sound familiar, but I honestly cannot remember exactly, but I think it might be Peggy. I'm making the mistake that I made last week of getting caffeinated tea instead of my usual evening caffeine-free tea. I'm not going to sleep tonight. This happened last week as well. It is fine. I just go with it. I wanted white tea. Not much caffeine, but caffeine nonetheless. So, during inflation, we have the event horizon of the universe. This is something we always have. And this kind of sets the patch of the universe that has time to talk to each other. Limited by the fact that nothing can travel faster than light in a vacuum. So if we want this part of the universe and this part of the universe to talk to each other, they need to have time to send each other information. If we're talking about something that happened when the universe was very young, it doesn't take long for light to travel around in a small place. But as things get bigger, it takes longer and longer for light to travel around. So the amount of the universe that we have that could talk to each other kept growing and growing and growing. So during inflation, this kind of event horizon, which we call the Hubble radius of the universe, starts growing. And I'm deliberately using the term event horizon because it's very, very similar to how we think about a black hole. Black hole has an event horizon around it. Once you reach the event horizon, there's no coming back. Now, here we're thinking about kind of the opposite. Anything that could communicate with something else needs to be within the same event horizon. During inflation, this event horizon grows very, very quickly, to the point that some of these things, some of these waves that are being stretched can be pushed beyond the event horizon. So these waves get pushed beyond the event horizon. They get stretched so much that this part of the wave and this part of the wave are no longer in causal contact. This means they are technically further away than what could give each other information. When inflation stops, it stops growing exponentially. These stop getting stretched, but the event horizon of the universe, this Hubble radius, continues to grow at a much slower speed. Again, if we go back to the standard picture, we can see that after inflation, things continue to expand, but a lot slower. During this time, anything that got pushed beyond the event horizon, because it was accelerating so fast, the event horizon couldn't keep up. At this point, they can come back inside our event horizon. So these are things that were in causal contact in the early universe, which meant they could exchange information. They froze out when inflation finished, but as the universe continued to expand, they came back in. But they are still connected. They are still the same wavelengths. They just got stretched beyond the point where they couldn't be affected by anything, and then they came back. Now, this is really important because this means that these quantum fluctuations go from being a quantum thing to being a classical thing. Now, if they're quantum, they're described by randomness. And this is very cool because these quantum fluctuations were completely random. They were distributed randomly, but once they come back into the event horizon of the universe, or the observable universe, they become classical. So this means that we have all of the advantages of a quantum fluctuation, meaning completely randomly distributed, but also they can now be described by classical physics. So this is very cool, because the overall effect of this, we often consider the universe to be a background universe where you have different species interacting. You have a fluid of dark matter, you have a fluid of protons, you have a fluid of electrons, you have dark energy also as a species. We consider these as the background things in a universe that is expanding and growing, a universe that is overall homogeneous and isotropic. This means that the universe looks the same in every direction we look, from wherever we look. Isotropic means it looks the same from wherever we look. There's no privilege point. This is our background. This is our solvable universe. Now, on top of this solvable universe that we can describe with Friedmann's equations, with Einstein's general relativity, we now have these perturbations that came from the wavelengths being stretched during inflation and then re-entering the horizon. This is going to leave random perturbations throughout the universe. So this is where we use perturbation theory. Inflation has happened. We have these tiny, tiny effects that left the universe, or didn't leave the universe, they left the observable universe. After inflation, they could come back in. They retained some of their original statistical properties, but now they are things we can describe with perturbation theory. So we start with the quantum fluctuation. We stretch it to a ridiculous size. It gets kind of sent to timeout. Then it comes back inside the universe. And suddenly it is a classical thing that we can describe as a perturbation. So now we have our background universe, where we have everything happening. This is our solvable universe. This is our basic bland bread. And now we have the perturbations that have come back in, which are the seeds we're adding to the bread. And this is where we're going to use perturbation theory. Just a comment from Outlook that you loved how I've explained this section. Great, that is good to know. Thank you. You know, these concepts is always hard for me to know, because I don't have a live audience. It's always hard to gauge the reactions. So I really appreciate it when you tell me that things make sense or things don't make sense, because then I can adjust what I'm saying based on the comments. So I do appreciate you telling me that it makes sense. Thank you. If it doesn't make sense to anyone, please do let me know. Okay, so where are we now? If we take up this map, we look where we've reached the point kind of like end of inflation. At this point where we've passed the end of inflation, we have a universe filled with the background effects and the perturbations on top of these background effects. What these perturbations actually look like are just regions where, at this point, what are they perturbations of? They are perturbations of space-time itself. They are what we call metric perturbations, which just means space-time itself has these tiny perturbations imprinted. So at this point, we have our background universe, we have our tiny perturbations. These perturbations are regions of the universe that are slightly more dense and regions of the universe that are slightly less dense. And these perturbations can be described by two parameters, basically, which are related to inflation. These two parameters tell us how many perturbations were produced, what the average size of these perturbations is compared to each other. Sometimes we might produce perturbations, if we think we can have these fluctuations, some small, some big, when they get stretched and leave the universe, some will be small, some will be big, some will be bigger. They'll all be bigger than they started, but they all start at a different size. So we have two parameters describing these initial fluctuations, these perturbations. One of them is how many perturbations we produced, and the other one is what was the ratio of small perturbations to big perturbations? Were they produced in similar amounts? Were there more big ones? Were there more small ones? How did this work? Two parameters, the amount and how many big versus small ones we had. This is everything we need to describe these perturbations. Comment from John here. So quantum perturbation theory is directly related to CMB perturbation theory because the quantum perturbations grew into the cosmic perturbations. Yes, exactly. So there was a reason I led with quantum perturbation theory before jumping into cosmological perturbation theory, because they are connected. We are talking about quantum perturbations in the early universe. These then become classical, so we can then throw them into cosmological perturbation theory. On face value, quantum perturbation theory, small world, cosmological perturbation theory, universe, but the origin is the same. And this is cool. Okay, so we've reached the end of inflation. We have these tiny regions of the universe where we have more density. We have tiny regions of the universe where we have less density. Just the overall space-time itself has overdense regions and underdense regions. If you've seen any of my streams about primordial black holes, where I talk about maybe the universe had regions that were so dense in the early universe they could have directly formed a black hole, these are the perturbations we're talking about. It's all connected. So what happens now? Well, now we have things inside the universe. We have dark matter. Dark matter breaks away from everything else pretty early. It's just going to do its thing. We have protons, we have electrons, and we have photons, which are particles of light. Now, all of these things, since I mentioned metric perturbation, do we choose the FLRW metric or something else? FLRW. So this is just the way we explain the space-time of the universe. Like, what does space-time look like? There are several different mathematical descriptions of space-time, and the most commonly used one is what is known as the Friedmann-Lemaitre-Robertson-Walker metric, discovered by these four, or developed by these four physicists, Friedmann, Lemaitre, Robertson-Walker. And this is generally our solvable system. And then we perturb this solvable system. So we have the solvable part, the basic bland bread, and the seeds that we're throwing on top of it. Later on, you'll realize why I've used this analogy of bread and seeds. I'm very proud of this analogy, by the way. You'll see why later on. So we have dark matter, we have protons, electrons, we have photons, particles of light. Now, all of these do feel gravitational effects. If we have perturbations of the metric, perturbations of space-time, this is going to lead to a perturbation of gravity, which means the dark matter, the protons, the electrons, the photons are all going to cluster in the regions where we had an overdensity. So we have our background universe, which is flat, not flat. Let's imagine we have our kind of calm background universe. On top of this calm background universe, we have these tiny vibrations. We have some regions where you're going to have less density, some regions where you're going to have more density. And this then starts a kind of snowball effect. In regions where you have an overdensity caused by the metric fluctuations, these perturbations, these quantum fluctuations that glue, whatever you want to call them, this is now where you're going to start accumulating dark matter, protons, electrons, and photons. And then if you have more matter, the overdensity grows. Put more matter in, the overdensity grows. And this is where this effect can start happening. Is there imperial perturbation too? I guess, yes. We talk about metric because we're talking about the metric of how we describe space-time. But yes, it took me a minute, but I appreciate that joke. Is perturbation theory easy to graph? Does it equal proximity? Thank you for the comment there, John. Yes and no. So perturbation theory is easy to graph for some things and difficult for others. Going back to what I said before, if you want to talk about particles interacting, this is something you can literally draw a picture for. It's a Feynman diagram, and you can use Feynman diagrams to explain perturbation theory in quantum physics. So sticking with FLRW, our description of the metric of space-time, is that it describes a completely homogeneous universe, and then you describe perturbations from that norm. Exactly. So FLRW is it's kind of the mathematical description of space-time itself. And here we can have homogeneity and isotropy as being the background, and then these perturbations or anisotropies as being the differences. So anisotropy means a lack of isotropy. Isotropy means something looks the same in every direction from wherever you look. You can have perturbations that are not directly anisotropies, but usually we use the two to mean a similar thing. So perturbations are specifically things we described with perturbation theory, whereas anisotropies, right? I could say my wall is white except this anisotropy up here. I would call this an anisotropy and not a perturbation because it's not part of the solvable system. This thing up here is just something that is breaking the isotropy or the isocolor of my wall. So isotropy would mean everything here is white. Anisotropy is this guy up here. If I want perturbations, then I'd have to look at the fact that this wall is textured. And these tiny textures are the perturbations. So there's a slight difference. This goes back to the question asked before of anisotropies versus perturbations. Similar but different. So FLRW describes a homogeneous isotropic universe, and we throw perturbations on top of that. Okay, so we have our universe where we have dark matter, we have protons, we have electrons. Dark matter is just there doing its own thing, but it is feeling this gravitational presence. Dark matter, protons, electrons, photons, particles of light. And now my favorite story of the universe. The universe is growing, the universe is cooling down. Now, at some point, it becomes easy or easier for the protons and the electrons to combine together. Once the electrons and the protons combine together, they can form the first hydrogen, the first atoms of the universe. You have protons, you have electrons. So in the early universe, you have dark matter in these overdensities doing its own thing. It's going to be everywhere, but there's going to be more of it in the overdensities coming from these quantum effects that grew during inflation. You have protons, you have electrons, you have photons, particles of light. Dark matter is doing its own thing. The other three are constantly bumping into each other. The electrons bump into the protons, the photons bump into the electrons. This keeps happening. As the universe cools down, the protons and the electrons combine together to form the first hydrogen element. At this point, the photons can't really do much. So the photons are going to break away. They're going to escape, and they're going to start traveling freely throughout the universe. These photons, particles of light, have been traveling freely ever since. Today, they make up the oldest light in the universe, the cosmic microwave background radiation. This is what we see when we look in any direction in the night sky behind everything else. There is this residue afterglow. These are the photons that broke away in the early universe. These have approximately the same temperature of 2.7 degrees Kelvin. That's minus 270 degrees Celsius, minus 440 degrees Fahrenheit if you want freedom units. Anticipating CMB picture was coming, it was coming. So the photons broke away, they started traveling freely throughout the universe. They have the same average temperature, but not exactly the same temperature. There are photons that are slightly warmer and slightly colder. Very, very tiny differences. We're talking about a 1 in 100,000th difference of a degree here. Really, really small. You have to go to the 5th digit to find a difference. So what caused these orange photons, blue photons? Let's go back to our overdense universe, underdense universe. We have our background solvable system. We have the perturbations on top of this, where we have overdensities and underdensities. Where there's an overdensity, before the photon can travel freely throughout the universe, it needs to escape this big overdense region. The more density, the harder it is for the photons to escape. So the photons are going to lose a bit more energy escaping that first overdense region, which means by the time they reach us today, 13.5 billion years after escaping these overdensities, they are going to be slightly less energetic. They're going to be slightly colder, which means when we look at the CMB, the blue photons here correspond to less energetic photons, so they were in an overdense region in the early universe. The orange photons were in a less dense region of the early universe. They didn't have to use as much energy to escape, and since then, by the time they reach us, they have a bit more energy. So these tiny, tiny, tiny temperature differences are caused mainly by these overdense and underdense regions in the early universe. Why are those photons still around and not absorbed somewhere or the other? Is space that empty? Yes, mainly, but also in order to absorb or emit a photon, you need it to be at a similar approximate energy or have a specific energy. If we consider these photons were produced 380,000 years after the Big Bang, after the end of inflation, there's quite some time before the first stars appear, before you can add anything else that's going to absorb or emit these photons. So by the time gas clouds appear that could absorb or emit these photons have such a low energy that they basically don't interact with much. They are still going to experience some interactions, but not many, because they already froze out at this early time. When I'm talking a lot and not drinking enough, when the universe became cold enough for the protons and electrons to combine together, at that point, the photons are no longer energetic enough to play a role in that that interaction. So those photons just are not energetically at the right level now to have any interactions, which is why they are largely untouched since that event and today, because they already lost a lot of their energy. The rest of the universe is at a different energy by now, so the photons don't really interact with much. So when we look at this map today, we have the blue regions, which correspond to the overdense regions in the early universe, and the same with the orange ones corresponding to the underdense regions. However, it is not that simple. That is the main effect, but there are another two effects that contribute to these temperature differences. One of them is the one that John just very nicely pointed out here in the comments. As these photons travel towards us, I'm going to use my trusty slinky, getting its mileage today. As these particles of light are traveling through the universe, their wavelength is going to be stretched. They experience Doppler shifting or redshift. So we have several effects when we look at the CMB, the cosmic microwave background radiation. We have the overdense, underdense regions in the early universe. We have the redshifting or the gravitational redshift, the Doppler effect of the photons traveling towards us. And then we have another cool effect, which is known as the integrated Sachs-Wolf effect, which is a technical word, but some of you might remember I did a whole stream about this some time ago. I talked about it in depth at some point recently being in the last year. The integrated Sachs-Wolf effect is what happens when these photons feel the gravitational presence of other things in the universe. Now, even though these photons might no longer interact with electrons or with other things like that, they are still going to feel gravity wells. Usually, if a photon is traveling through the universe, imagine you have a galaxy, the photon is going to enter the gravitational well of the galaxy, so it's going to gain energy. Then it's going to have to escape the gravitational pull of the galaxy. It will lose the same energy that it gained going in. However, if during the photon traveling through this galaxy, the galaxy is stretched due to the expansion of the universe, the amount of energy the photon is going to gain and lose is going to be different. So this is going to contribute. So when we look at the CMB, there are three main things at play here. There is the overdense and underdense region. There is, of course, four things at play. The first one is the whole idea of the photons and the baryons, or the protons and electrons interacting. There is the intricacies of their interactions. This is going to lead to a lot of the statistical properties of this figure. But on top of that, we have the overdense, underdense regions in the early universe. We have the Doppler effect of the light traveling towards us, or the redshifting. And we have the Sachs-Wolf effect, where photons gain and lose energy because of gravitational effects. So comment from James here, are there only two colors because the differences in temperature are so small? No scale. It is actually a scale here. I honestly don't know why they went for a scale that goes from blue to red, because it is quite difficult to see. But if you look closely, there are light blue, there are yellow ones, there are almost white ones. So it is actually a sliding scale. It is a color map. It just looks like blue and orange, but it is actually a sliding scale. Comment from Perth, if they don't interact much, how do they get detected? Surely the second can't happen before the first. Excellent question. The cool thing is we can tune our detectors to have the right energy to absorb these photons. Not many things in the universe are going to naturally have the low amount of energy we need to absorb the CMB photons, but we can tune our CMB missions to have the exact detector the exact properties it needs to be able to absorb these photons. My tea's getting cold. I really should drink the tea because it's a good tea. And tea is getting cold, which is, of course, a crisis. Also, tea will help me stop coughing. So even though the photons themselves don't experience many interactions in the universe, we can fine-tune our detector to the exact energy that we expect the photons to have, which we know, and then we can use that to measure them. So going back to the CMB, I've mentioned before that this map gives us the statistical properties of the early universe. The reason for it, you'll remember I said there are quantum fluctuations leave the universe as a random quantum fluctuation, and then they re-enter as classical. This means that this map here, because we can trace back the main differences here to the overdense and underdense regions, the statistical properties of this map are going to be very much well described by quantum physics in a classical realm. So when we look at this map, we're looking at a snapshot of what the universe looked like when these photons broke away. When we actually break it down and look at the individual temperature of the photons, or the how many blue spots there are and how close together the blue spots are, what we're actually looking at is what these fluctuations, these perturbations looked like in the early universe. And I'm going to come back to this in a sec. One question here from Ben. So the only source of photons in the universe is proton and electron interaction. Can electrons produce photons on their own? So most of the photons in the universe were produced in the first few minutes of the universe when particles and antiparticles annihilated. If we had matter and antimatter, this annihilated and produced photons. And these are most of the photons we have today. Most of the CMB photons came from that. On top of that, you can produce photons in stars and anything that's emitting energy. But the initial photons in the universe that make up the cosmic microwave background radiation come from matter and antimatter annihilating in the early universe. Okay, so because we know that these photons were interacting with the protons and electrons, and the protons and the electrons were following the underlying dark matter distribution, and all of this was following the perturbations, which were quantum effects that we can describe through perturbation theory. When we look at this figure, we can get the statistical properties of the universe. So from this figure, we can pull out our standard model of cosmology. And our standard model of cosmology has 6 parameters. 3 of them you're used to. 3 of them are related to the amount of normal matter, the amount of dark matter, the amount of dark energy. These are the numbers that we get in the standard pie chart. These numbers come directly from the CMB. So we use the CMB, we get these numbers. 3 of the parameters of our standard model of cosmology: amount of normal matter, amount of dark matter, amount of dark energy. A 4th parameter that we have is when the first stars turned on. Now, we can measure this because when the first stars turned on, they injected energy into the CMB. This slightly modified how the photons behave, more to the point, the direction in which the photons vibrate. So we can measure that. And then there's the other 2 parameters, which I always just say are related to inflation. Those other 2 parameters are the ones I mentioned before: the amount of primordial fluctuations and whether we have small or big primordial fluctuations. So this is how we get our standard model of cosmology. We can tell the story going from quantum fluctuations in the early universe, inflation, overdense or underdense regions, to anisotropies, temperature differences in the CMB today. We tie it all together in a neat bow called the standard model of cosmology. But the story doesn't end here. There is still one main piece, I promised: origin of galaxies, and that is still missing. Comment from Beth here: isn't all lasers solely light from electrons changing their orbitals and not proton-electron interactions? Yes. You don't really produce photons by proton-electron interactions, but they are involved in that. But most photons you can produce by dislodging electrons. If you shine a light on an electron, you can get it to jump to a different orbit. When it drops down, it will send off a photon, so you can produce the photons. Comment from John here: is the CMB power spectrum basically showing how many temperature perturbations there are of each possible angular size? I really, really like that question. So when we look at the CMB, we don't just care about how many spots are orange, how many are blue, how these are distributed. We can actually make a plot of this. This is what the anisotropies, the temperature anisotropies of the CMB look like. Here is where these big peaks are called the kind of vibrations that you see, these oscillation patterns. This is caused by the interplay of baryons causing pressure and pushing things outwards, like the photons trying to go outwards, and gravity pulling things inwards. This creates this kind of oscillation pattern in the early universe. But here you can directly see the amount of dark matter, dark energy, normal matter. This will affect how each peak looks like, because what this is showing us is basically how many perturbations there are on specific angular sizes. Now, there is a very cool thing. This picture has an overall tilt. You can see it's basically not tilted, but you could imagine this whole thing could be tilted one way or another. If there were more perturbations on large scales, this would be tilted like that. If there were more perturbations on small scales, it would be tilted like this. This is one of the parameters we get for describing inflation, or describing these perturbations during inflation. If you have the same amount of big and small ones, you get an approximately flat spectrum, which is what we have. The overall scale, the starting point for this picture, that is given by how many perturbations were produced in the early universe. It is way too hot for such an energetic stream today. Okay, I see people here discussing how lasers are done. I'm definitely not going to go into that today. That is very much outside the scope of this stream. Whew, just need to catch my breath because I'm talking very quickly, not drinking enough. And it is like 28 degrees inside my apartment. One more piece of the story to go. I mentioned we have this background universe. On top of this background universe, we have our tiny perturbations, our overdense regions, our underdense regions. These provide the kind of foundation for the CMB. But I mentioned the dark matter is also there. The dark matter is also playing a role. Dark matter, gravitationally attracting object, is going to be in the overdense regions of this early universe, together with the first elements, the first hydrogen atoms that are formed. I see people here from West Pennsylvania and everything. Great to know where you're coming from. Always nice to know where you're watching from. The power spectrum is a Fourier transform of the CMB map. Yes, there are Fourier transforms involved here as well. No, there's no aircon in my apartment because Finnish houses are not designed for heat waves. Finnish homes are designed to keep the heat in winter, and then in summer it becomes a problem, and all of my windows are south facing. So by now my apartment has just reached a point where it's kind of warm. Because I'm being very energetic with the stream, I'm just feeling slightly flustered right now because of the heat. And of course I cooked today, which heated everything up as well. Okay. We have our, it's 21 degrees outside. The problem is inside because it's been about 28 all day. Inside it got really warm. Yes. Okay, so I don't want to go into Fourier transforms today, but a Fourier transform is involved when we go from the perturbations mathematically, when we try to go from the perturbations to the temperature differences around us. Here is where we will use a Fourier transform. So we have our background homogeneous bland bread universe. We have these overdense regions, the seeds that we've thrown in. We have the underdense regions. Once the photons that make up the CMB have broken away, what you're left with is the background universe with ups and downs, overdense, underdense regions. Inside the overdense regions, you have dark matter, gravitationally attracting, and you have the first hydrogen atoms. So what happens if you put a lot of hydrogen in one place and you increase the density and you increase the gravitational force? You're going to pull things together, and if you pull things together enough, you can start stellar fusion. So then you have hydrogen clouds that are going to gradually pile up and pile up and pile up in the overdense regions. You're going to form the first stars in the overdense regions. As the universe grows, again, these overdense regions continue growing. The more time passes, the more they have this kind of snowball effect. It was overdense, you get dark matter and hydrogen there. Now it's more overdense, so now it has a bigger gravitational presence, so more things can fall in. Then you have dark matter, you have the first stars starting to form. You put enough stars and dark matter together in one place, and you will get the first galaxies. Give it a bit longer, you get galaxy clusters. So the same overdense regions that give us the blue spots and orange spots, the cold spots and hot spots on the cosmic microwave background radiation, are also providing the scaffolding for galaxies to form. So galaxies form on the scaffolding of dark matter, which fell inside these overdense regions. So if we take our background universe, with these perturbations, we have our bland bread universe. We threw some seeds in. These seeds are now the seeds of the galaxies. Haha, there's where my analogy was going. So these overdense regions set the scaffolding, or set the groundwork for dark matter to fall in. The dark matter falling in sets the groundwork for the galaxies to form, and this is where you start to form your cosmic structures. So then when we look at the universe today, we see this amazing cosmic web. I'm trying to find a specific image. You should all know which one I'm going for by now. the cosmic web as measured by DESI, the Dark Energy Spectroscopic Instrument. Every dot here represents a galaxy. These galaxies are formed in the overdense regions. The voids in between galaxies correspond to the underdense regions. So the same theory that we use, the same perturbation theory, the same mathematical description we use can allow us to explain why there are temperature differences in the CMB and why there are galaxies in the universe. Unfortunately, we can't just put the cosmic web and the CMB on top of each other to find these regions because of everything that's affected the CMB since it was produced. Since the CMB was produced, we have the Doppler effect, we have the other gravitational effects, we have the integrated Sachs-Wolf effect, we have lensing. So they're not a one-to-one match, but the underlying idea is the same. So we can tell a story going from quantum fluctuations in the early universe that then grow, they go outside of the observable universe, they come back in, they become classical perturbations that we can describe with perturbation theory. And then we can use perturbation theory to explain how these overdense regions became more overdense, how this led to colder spots on the CMB, and how this set the seeds for galaxies to form. Without these cosmological perturbations in the early universe, we might not have galaxies today. We might not have enough overdense regions to be able to form the scaffolding of dark matter and everything on top of that. So when I say I love perturbation theory, it's because it underpins the entire history of the universe. This is really cool when we think about it, that we can use this mathematical framework, we combine it with the FLRW metrics, or our description of the universe, Einstein's equations, we throw perturbation theory on top, and suddenly we've got the story, the history of the universe, told through these tiny, tiny fluctuations that then give us the CMB and cosmic structure. It's amazing. It's really, really cool when you think about it. Okay, questions. An electron would have to lose energy to get bound by a proton to begin with if they didn't have a direct collision. Yes, that makes sense, yes. So was our galaxy made of an opium poppy seed? Who knows? But yes, the seeds that we're sowing in our bread to have this fancy bread are the seeds that set the galaxies in motion. So basically, perturbation theory is at the heart of every single structure of the universe. Yes. In order to describe why there are structures in the universe, we use perturbation theory. It's amazing. A comment from John here. How do you think the JWST findings will affect the picture of galaxies growing from CMB fluctuations? I don't think it will affect this overall description of overdense and underdense regions. What if JWST has indeed found galaxies older than what we thought? It just will affect the time at which the first stars began to form, the time at which there was enough hydrogen inside these overdense regions to ignite stellar fusion to start this whole process. But it shouldn't dramatically change this story. So now the big question is, how far can we push perturbation theory? Where does it stop being a good description? And I want to go back to the idea that I started with of the bread. And if you're just throwing a handful of seeds on, you're still making the same bread and you're just adding this perturbation on top of the solvable system. However, if you are adding so many seeds in that it changes the whole composition of the bread, you can no longer do perturbation theory because the change you're making is too big compared to the base solution. So you always need the change to be small compared to the base solution. Now, I mentioned at some point that perturbation theory in cosmology takes a universe as being homogeneous and isotropic. It looks the same in every direction from wherever you are. There we can use perturbation theory. If I take this picture, when we take a step back, every patch of the cosmic web looks similar to every other patch of the cosmic web. We can use perturbation theory to describe this. However, when we start getting into individual galaxy clusters, individual galaxies, the universe can no longer be described as a bland bread with seeds, because the seeds, the galaxies, the individual structure is more important than the overall background description of the universe. So as these cosmic structures get bigger and bigger, they can no longer be ignored. And this is especially true if we focus on a small patch of the universe, like our local neighborhood, a couple of clusters, even Laniakea, which is our local kind of group of clusters of galaxies. Now, at this point, perturbation theory breaks down, because if we're looking at a patch of the universe like this, and everywhere you look there's a galaxy, you can no longer say this is homogeneous and isotropic. The perturbation is now as big as the classical solution that you're starting with. So you can no longer use perturbation theory. This is why when we look at the cosmic web, even though we can explain its origin with perturbation theory, if we want to do the whole description of the cosmic web today, perturbation theory is not sufficient. Perturbation theory sets the starting points, but if we want to do this today, we have to do simulations. And this is where we do things like the Millennium simulation, the Illustra simulation, these things here. This is the Flamingo simulation, and these are the simulations of how galaxies evolve on small scales. The reason we need to do complicated simulations is because the structure of the universe becomes so big at these scales, or so significant, that it's no longer a correction to the background universe. So even though we can use perturbation theory to set the seeds for galaxies, if we want to explain how that then progresses properly into the cosmic web with all the detail that we have in this simulation here, we need something more than perturbation theory. So going back to a question that Arlok asked me at some point, can we use perturbation theory to talk about the sigma-8 tension? So the sigma-8 tension is a discrepancy we get, or a difference we get when we try to ask the question of how does matter clump together on small scales. Depending how you ask this question, you get slightly different answers. Now the problem is, because we're talking about matter clumping together on small scales, we're in what is known as the non-linear regime. Perturbation theory is not enough. Perturbation theory breaks down. At this point, we need something more. So even though perturbation theory is a very powerful mathematical framework, it gets us started, it provides this whole picture, it is not the full story. And at some point when the effects become too big, such as when we're looking at individual galaxies or galaxy clusters, at that point, the region we're considering has so much perturbation that you can't just say it's a solvable thing with some random seeds thrown on top. So when we're looking at small things like the sigma-8 tension, at small scales, lots of clustering happening, you can't use perturbation theory. So to answer your question, no, we cannot use perturbation theory alone to talk about the sigma-8 tension. But we can use perturbation theory to tell a story going through inflation, quantum fluctuations, the CMB, and the existence of galaxies today, which is pretty cool when you think about it. Technical question from the Sitter Space. Can you elaborate a little bit on what is photometric and spectroscopic redshifts? Not today, no. That is a cool question, but I'm going to save that for another day, perhaps. The difference between photometric and spectroscopic. So related to the way the photon... So redshift is when you have... I'm going to give a very short answer and perhaps elaborate some other day. When you have a wavelength traveling throughout the universe, this can be stretched or condensed, stretched or compressed. When we're talking about photometric redshift, what we're talking about is the redshift caused by an object moving through the universe. And when we talk about spectroscopic redshift, what we're talking about is an object moving due to the expansion of the universe. Slightly different nuance, it depends which part you're doing the redshift on. So it is a very technical question. That's my very short answer, but I won't go into more detail today, but I've made a note of it so we can go back to that some other time. Follow-up from Arlok here. So perturbation theory is valid for extremely high redshift, and numerical simulation is the answer for lower redshift. Exactly. When you get down to what's happening in the universe today, perturbation theory is no longer a good description. But perturbation theory tells the story from inflation, quantum fluctuations that become classical and freeze in, and then give us overdense regions, which might lead to primordial black holes, leads to the CMB, and leads to there being galaxies today, which is kind of a lot to ask for perturbation theory to do. You know, it's very, very cool. It's amazing to think that we can have this explanation, we can draw this picture, starting in the very early universe, going through the cosmic microwave background radiation to where we are today. So, you know, this stream was motivated by me dropping hints about perturbation theory recently and saying I should just do a whole stream about the topic. Now, describing these perturbations mathematically is extremely difficult. We have this idea, we have the solvable part, we have the perturbations. Understanding the story that I've told today of the perturbations, the transition to classical, all of this story, if you want to describe it mathematically, it's an 8-week-long master's level course called Advanced Cosmology or Perturbation Theory. My PhD topic was mainly about studying how different particles interact in the universe, what happens if we change this, and all of that comes down to perturbation theory. If we're talking about an overdense region of dark matter and an overdense region of baryons, and these can somehow talk to each other, that affects this whole story. So a lot of what I did during my PhD was figure out any new problem, any new model in the universe, how can I describe this with perturbation theory, and then how can I implement that in a cosmological code? So perturbation theory underpins a lot of modern cosmology, and it is a very powerful tool. And it is something that really today I've just touched the surface without going into the mathematics of it. But if you think the story's cool, I agree, it's a very cool story. The mathematics of it is even cooler. The fact that we can mathematically describe everything I've told you today is kind of cool. And it's really fun. You can't see the third line on my shirt. Yes, I showed my shirt at the beginning. Can't even think straight. I know that with the camera angle, it's cut off, and I'm just like, oh, I can't even with this heat. There we go. Now I can actually use the shirt like that. Okay, comment from John here. Is the modern universe still considered isotropic and homogeneous? On large scales, yes. If I look at the CMB, it looks pretty homogeneous and isotropic on large scales. If I look at the cosmic web, it looks pretty much the same. Any patch of the cosmic web is the same. But it's when you go into specific details that it breaks down. I just realized that the letters are a mirror, so you said I can nod instead of I can't even. Yes, I just realized that, Fortunine. Thank you. That is very funny. I am amused at that. It took me a minute to realize that. Yeah, so the universe is homogeneous and isotropic on large scales, and that is still a very good description of the whole universe. But when you start picking up individual patches of the universe, then that breaks down. But yeah, we can describe the universe as a bland loaf of bread with a bunch of seeds thrown in to a point. And I think that's very, very cool that we can tell this story. So also, while preparing for this stream today, a couple of years ago, 7 years ago actually, I participated in a science slam, and it was a 3-minute science slam where you have to explain a concept in 3 minutes. And for some reason, I decided to tell this whole story that I've told today in 1 hour and 20 minutes. I tried to tell that story in 3 minutes. If you want to watch my science slam, it is on YouTube. It is called Taking the Fingerprint of the Universe. If you put that with my name in YouTube, you will find it. It's also linked to on my webpage, which is dchooper.com. And there you get the 3-minute version of this 1 hour and 20 minute stream. So if you want the too long didn't read version, go look at my science slam from several years ago. Also, it was very clear to me when preparing this stream, I was like, this is going to take me over 1 hour. I was wondering how did I think it was a good idea to try to condense that into 3 minutes? And no wonder that felt very packed and very dense, because this is a cool story and not a story. This story deserves at least 1 hour. So, okay, that is perturbation theory in a nutshell. You take a problem, you break it down into the part you know, plus some small effects. And we can use this to explain everything from quantum physics to the motion of the moon around the Earth, to how you make bread, to the whole history of the universe. And that is very cool. So perturbation theory is a mathematical tool. It's a mathematical construct. It is our way of trying to make sense of things. It is a very powerful tool that we have. And yes, that science slam a few years ago is actually where I bought this Slinky toy for that science slam, because we were allowed one prop. And it had to be a prop you could carry on stage. So I took this as my prop, as you saw today. It's very useful. About 1 minute into my science slam, I was nervous. I had this in my hand. I pushed it down to my wrist for safekeeping, and it got stuck. So then I was on stage, and you can see the point in the video where I try to get my Slinky toy off, and then I'm like, oh, whoops, it's stuck. And then I do the rest of the stream with my prop stuck on my wrist. And then the judges at the science slam made the comment of, you didn't use your slinky toy much. And I was there like, yeah, it got stuck on my wrist. That's why I didn't use it much, because I'm a bit of a muppet. But yes, today it did not get stuck. I learnt my lesson, never put slinky toy on wrist in a rush, because it will absolutely get stuck. So yes, that Science Slam is on YouTube. You're welcome to watch it if you want. It is very funny. Watching it back now, I think it is very funny. Comment here, when does or if the Planck field affect particles? That's when you have to go to really, so the Planck field is like the lowest thing we can break things down to. And at that point, you have to go to really, really tiny sizes and energies in the universe. So yeah, perturbation theory underpins a lot of modern physics. It tells us a lot about quantum physics. We can use it to explain particle interactions. We can use it to explain the motion of the moon around the Earth. And we get the entire history and evolution of the universe, which is pretty cool. So hopefully I've convinced you that perturbation theory is amazing. The universe is indeed perturbed, but that is a good thing, because it helps us tell the story of the history of the universe. It took me 1 hour and 20 minutes, but I did not show a single equation as promised. Perturbation theory, mathematical tool, done without the mathematics. Hopefully, now if you're motivated, you'll look up perturbation theory and you can find 1 hour lectures by people doing it mathematically, but it assumes a lot of pre-knowledge of mathematics. But that's the basics. Perturbation theory, in a nutshell, being 1 hour and 20 minutes. If you want the even nuttier nutshell version, there's a 3-minute version on YouTube from a few years ago. I'll post a link somewhere. Whew, okay, that was very fun. I at least had a great time. I hope you all had a great time as well. I saw someone just now make a comment saying you have to watch this stream a few times because there's a lot of new concepts. That is true. There's also, I hope today I've given you a deeper understanding of the cosmic microwave background radiation. You know, this is my favorite thing in the universe, the CMB, as some of you might have noticed. And I feel like every time I talk about it, there's stuff that I leave unsaid. You know, there are overdense and underdense regions. Where do these come from? Well, today we went into detail about where exactly this comes from. And hopefully that next time I show the CMB, you'll be like, there's perturbation theory hidden there. It's fun. It's cool. I love it. Thank you. I see a lot of people saying I explained it well. Thank you. Thank you for the nice comments. I really, really do appreciate them. I had a lot of fun with this. I hope you all did too as well. And despite what I said last week, my plans have changed. So I'm no longer traveling next week. It all got a bit chaotic. I'm no longer traveling next weekend, which means there should be a couple of cosmology next weekend. There will be a longer break later in August, but there should be a couple of cosmology next weekend. So that is 8 p.m. if you're in Finland, 7 p.m. if you're in the rest of Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is in your own time zone. Please do click there if you want to know. You can also subscribe to the YouTube channel or to the Twitch channel, Cup of Cosmology, on both platforms, where you can figure out, where you can get notified for the next streams. If you follow me on YouTube, if you follow me on Twitch, you will be notified 30 minutes before the next stream starts. There is also an Instagram account you can follow if you are so inclined. That is also Cup of Cosmology. And on the Instagram account, I just post teasers of what's to come. Sometimes I post highlights of what was discussed. It's still not used a lot, but there is an Instagram account. You're welcome to follow that as well, Cup of Cosmology. Basically, on every social media, if I'm there, it's Cup of Cosmology, except Mastodon, where it's DCHooper91_Cosmo. Comment from Lethargo here, it will be amazing if we can ever get enough neutrino and/or gravitational wave observations and resolution to see observations from even before the CMB. That would be amazing. Someday that might happen. I really hope that's going to happen someday. So, okay, almost an hour and a half today. This is setting a new record for the stream. I'm completely out of breath. My water's empty. I am going to go rest. But this has been great fun. I've really, really enjoyed it. I hope you all have as well. Thank you for all the comments, all of the interactions. I always do appreciate all of the comments, all of the questions, all of the interactions, people chatting among themselves. It's always great to see. Whew, out of breath. Definitely time to end this. Thank you everyone for joining. This really has been great fun. I hope to see you all again next week, same time as always. And I hope in the meantime, you will take care of each other and stay curious.